Hello everyone and welcome to Signals, Systems and Signal Processing with Wolfram U. This lesson will be on discrete-time Fourier transform. The discrete-time Fourier transform is the discrete-time counterpart of the continuous-time Fourier transform. It plays the same role in the discrete-time domain as the continuous-time Fourier transform does in the continuous-time domain. It gives us insight into the spectral content of signals and the frequency response of LSI systems. For a sequence x of n, the discrete-time Fourier transform is defined by the summation shown here. In general, it is a complex function of frequency omega. And given the discrete-time Fourier transform, the sequence x of n itself can be computed by evaluating the integration shown here. The discrete-time Fourier transform is an infinite series, and so it may or may not converge to a finite value. A sufficient condition for the existence of the discrete-time Fourier transform is that the sequence x of n should be absolutely summable. In other words, the sum of absolute values of x of n going from minus infinity to plus infinity should be finite. To prove this, assume that the condition is satisfied and x of n is absolutely summable. Then the absolute value of the Fourier transform will be equal to the absolute value of the summation according to the definition of the Fourier transform. And this is less than the value of the sum taken over the absolute values of each terms inside the Fourier transform summation. And since the absolute value of the exponential term is less than 1, the expression will be less than the sum of absolute values of x of n, which is a finite value. And so the Fourier transform exists. The discrete-time Fourier transform in rectangular form, as shown here, can also be expressed in polar form. The absolute value of the Fourier transform is called the magnitude function or the magnitude spectrum, and the quantity theta of omega is called the phase function or phase spectrum. The phase function is typically restricted to values between minus pi and pi. Now, the Fourier transform is periodic with a period of 2 pi. If omega is shifted by 2 pi, the Fourier transform will be equal to the expression shown here. Breaking down the exponential term and simplifying, we get x of e to the power j omega. And so the Fourier transform, the discrete-time Fourier transform, is periodic with period 2 pi. Also note that the frequency interval omega between minus pi and pi, or between 0 and 2 pi, is known as the fundamental interval of the discrete-time Fourier transform. As an example, let's find the discrete-time Fourier transform of the finite length sequence x of n as it's defined here. Let's plot the sequence to see how it changes over n. We could check first if the Fourier transform exists. Since the sequence here is finite length and finite valued, the discrete-time Fourier transform does exist, and so we don't need to check the condition for existence of the Fourier transform. Using the Wolfram language, we can directly find the discrete-time Fourier transform as shown here. Now, if we were to find the values using the definition, replacing the values of x of n, we get a finite summation, which can be expanded and simplified as shown here. As another example, let's find the discrete-time Fourier transform of the exponential sequence r to the power n un, where the absolute value of r is less than 1. First, let's check and see if the sequence is absolutely summable. The value here is finite, and so the discrete-time Fourier transform exists. To find it, we can use the Wolfram language using the function Fourier sequence transform and find the value. Or using the definition, substituting the sequence x of n and rewriting the summation so that it is taken over the base r e to the power minus j omega to the power n, we can simplify the sum as shown here, which matches the result obtained by the Wolfram language. Given the discrete time Fourier transform x of omega, for example, consider the discrete time Fourier transform of the sequence in the second example with r equal to 2 over 3. We usually plot the magnitude, sometimes magnitude is squared, the phase, or both of the magnitude and phase spectrums. And sometimes the real part and the imaginary parts of the spectrum might be of interest. Due to periodicity of the discrete time Fourier transform, it is common to plot the spectra on the fundamental interval only, either omega between 0 and 2 pi or omega between negative pi and pi. What is shown here is the plot of each spectrum for the fundamental interval between minus pi and pi, and here for the fundamental interval between 0 and 2 pi. For the plot of the magnitude of the discrete time Fourier transform, if we extend the domain, we can see the 2 pi periodicity. Also, for real signals, the magnitude has even symmetry. So it is sufficient to plot the absolute value of the Fourier transform on the interval between 0 and pi. Finally, it is common practice to scale the magnitude logarithmically and to use linear scaling on the frequency axis, as the normalized range is always between 0 and pi. This is what's called the Bode plot. Let's look at another example. Given the Fourier transform shown here m is an integer, let's find x of n, taking the inverse Fourier transform. Let's plot the magnitude spectrum over the fundamental half interval omega between 0 and pi to see how it changes over frequency first. And then using the function inverse Fourier sequence transform in the Wolfram language, we can find the sequence x of n. If we plot x of n, we have a sinc function as shown here. Now, using the definition, to find x of n, we replace the discrete time Fourier transform with its value. We take the integral and simplify to get the same value for x of n as we obtained using the Wolfram language. Now, periodic sequences do not satisfy the discrete time Fourier transform existence condition. For example, for the periodic cosine sequence, the sum of absolute values does not converge. However, periodic sequences do have Fourier transform, but they must be obtained indirectly using their Fourier series representation, and they're formulated in terms of Dirac delta function. To drive the Fourier transform representation of periodic sequences, first let's find the inverse discrete time Fourier transform of the periodic impulse train defined as shown here. Here is a plot of the function. The inverse discrete time Fourier transform gives us the exponential expression shown here. And this result gives us a relation between a complex exponential sequence in time, which is what we have here, and a periodic impulse train in the frequency domain. With this result, we can obtain the Fourier transform of any periodic sequence. Remember that a periodic sequence x of n with period n has the Fourier series representation shown here. If we take the discrete time Fourier transform of both sides of this equation, the discrete time Fourier transform of the exponential sequence will be the impulse train shown above. And so the Fourier transform of the periodic sequence x of n will be given as indicated here. As an example, let's find and plot the Fourier transform of the periodic sequence shown here, the sawtooth wave sequence. Recall from the previous lesson on the discrete time Fourier series that we found the Fourier series coefficients of the sawtooth wave with period n equal to 16 as shown here. We can list the values of the coefficients. And now using these values, the Fourier transform will be given according to the formula we obtained earlier. Here we show the results for the fundamental interval between 0 and 2 pi. In this lesson, we presented the discrete time Fourier transform. We evaluated the transform of several aperiodic and periodic sequences, and we obtained several transform pairs. We also showed that the discrete time Fourier transform has a periodicity of 2 pi.